Last thing we want to talk about with rational functions, I was able to talk about this a little bit in one of the classes, but not the other. That is finding the end behavior of a rational function. This end behavior is a little bit of a subtle thing. It's about what happens when you go way, way, way out, left or right. It's not evaluating at any particular point, but we've gotten a sense of what that does for polynomials. And the cool thing is that it's not much more complicated for rational functions. I do want to do 3 contrasting examples, but I want to show you how quick and easy it is. So the first example is exactly the same function we had before, but we're going to imagine what can we predict what's going to happen if we zoom way, way out in x, left or right, horizontally. What's going to happen to the y values? And so I've actually put it into standard form here. It's not factored anymore. It turns out it's much easier to, or it's rather easier to get it from this form than factored form. So factored form is great for intercepts and asymptotes. This form is better for end behavior. And the key is that when x is a huge honking big number, if it's like 1 billion, this is going to be so much bigger than this guy because I've got that billion squared that it's as if this doesn't even matter, to a very good approximation. And the 24, oh my God, not even close. 3 times 1 billion squared is so huge. Minus 18 billion plus 24 doesn't even matter. Similarly, the lower order terms don't matter on the bottom. You might recall that's exactly how I was justifying end behavior for a polynomial, saying it's as if the lower degree stuff doesn't matter. So we're going to say this is approximately equal to just the stuff with all the lower order terms on the numerator and denominator dropped separately. The leading terms on both always survive. That's going to be true in all 3 examples. It's just what happens after that. This happens to be an example where the degrees of the numerator and the denominator were equal, and therefore it completely cancels down to a number. Hey, so if this says that when x is really big, I'm approximately getting 3/7 for the y value, I think I've found a horizontal asymptote. And indeed, this is just the same function. You can see kind of I've squeezed it. I've made the x go from minus 50 to 50. You can see a little trace of vertical asymptotes, but I'm not emphasizing that anymore. Now I've put in the line where f of x, where y is 3/7, a little bit under a half. And notice that indeed that graph is getting closer and closer as I go out left and right to that y equals 3/2 value. So it's a cover-up method. It's super similar to what we were able to do with polynomials. It's just there's one more little cancellation step. And when these degrees are exactly equal, we will get this horizontal asymptote. Okay, so that's nice to know that it's such an easy method. And notice that the function totally does cross right in here. It crosses that asymptote. Remember, that's totally legal. Functions can cross a horizontal asymptote. All right, example 2, pretty random, but notice the difference here is the degree of the numerator is less than the degree of the denominator. Oh, I wanted that to be a surprise reveal, but let's just hide it for a second. Okay, so what do I get? This is, that's not what I wanted, approximately equal to, just do the exact cover-up method. It's really not hard. I'm imagining that the 11x minus 13, the minus 2x is just not even there. These aren't exactly equal. That's not what I'm saying. But I'm saying when x is large, they are very, very good approximations, and that gives me an idea of the end behavior. Now, how does that cancel down? That is, the 4 and the 9 don't do anything weird. Don't do funky things with those guys. But an x squared on the top cancels 2 of the powers on the denominator, and I get a 4 over 9x. Now, this is something that's a little new, although really not really new, right? It's very much like just one of our most standard graphs, the library function, f of x equals 1 over x. We know what that does. We know that when x is really big, and even in this example with the coefficient, the 4/9, when x is really big, this is going to get small, right? So this goes to 0 as x goes to either plus or minus infinity. So either direction, left or right, this thing's going to go to 0. So this is again a horizontal asymptote. So it's not as different from example 1 as you might think. but that that asymptote is special. It's y equals 0. It's the x-axis. That's really nice to know. Very, very often, it's an incredibly nice thing to know that if when you go left or right on a function, it basically dies. Just goes to 0. So that's what this graph is showing. Again, it's got some interesting vertical asymptote stuff in the middle. I'm not caring about that. I've got the x scale set to be really wide, and we see that those values seem to get really, really small. Yes, they really do. Notice the vertical scale. It's not even up to 1. This is like already down to like less than 0.1, less than 0.01. It's dying pretty well as we go left and right. So again, the main thing is the cover up, cancel to simplify as needed, and then just recognize that if I've got a leftover x in the denominator, then it's going to go to 0. So this will happen. This is actually really one of the nicest cases. Whenever the degree of the denominator is greater than the degree of the numerator. Okay. So that's a nice, that's a shortcut. Just looking at the degrees, if the denominator degree is higher, strictly higher than the degree of the numerator, you can guarantee that the asymptote is going to be y equals 0. The horizontal asymptote is the x-axis. So that's really the simplest case, if you will. The last case I want to give you, if you sort of paying attention, you might guess, hey, what if the degree of the numerator is higher than the degree of the denominator? Okay, well, we're still going to do our cover-up method. When x is a billion, it's still true that those leading terms are going to give me much bigger numbers than the other guys. So this is a very good approximation. Okay, the 2 and the 4 happen to cancel a little bit, might as well. Now, though, there's an uncanceled x in the numerator. And then I just go back and I refer to, I say, the end behavior of this function will match the end behavior of y equals 1/2 x. That's a monomial. It's just it's a very simple, this happens to be linear function. But even if it was x squared, x cubed, x to the fourth, whatever, we know those end behaviors, I hope, by now. And it's just going to match. It's going to be as if you had that kind of end behavior. So in this case, we get what's called a slant asymptote. And you don't need to memorize that. You just have to remember, do the cover-up, do whatever cancellation is appropriate, and then pretend that this is a problem from a few days ago where I just handed you a polynomial, in fact, a monomial. This is like problems from like mini quiz a couple quizzes ago, and I'm just asking for the end behavior of this. It will match. That doesn't mean that's exactly the same function. Notice you've got some wiggly here, some funky vertical asymptote stuff for small x's, but notice what happens when x is large positive, large negative. I've graphed y equals 1/2 x, that's the dashed line here, alongside this guy. It just starts to become more and more like this very simple function. So the story of end behavior for rational functions is really nice, even though the details and every single feature of a rational function can be quite interesting. It can have interesting asymptotes, intercepts, ups and downs, wiggles, all kinds of stuff. End behavior can never be any more complicated than at most what a monomial does, which might be like a square, a cube, might be linear like this guy. It's often the most absolutely simple horizontal asymptote, which is the x-axis, and it's easy to recognize that. That's exactly when the degree of the denominator is greater than that of the numerator. And a really pleasant situation is when the degrees match, and then it has a horizontal asymptote that's not 0, but that's still easy to find. It just ends up being the ratio of the two leading coefficients of the two polynomials. So, very nice story.